Mr. or Mrs. Chairman, thanks for your kind introduction. Good morning, everyone. I'm Zixin Zhang from Xi'an Jiaotong University. Today, my presentation is about the conceptual design and analysis of a novel system coupling hydrogen liquefaction with multi-energy liquid air energy storage. I will introduce it in these 5 sections. The first is about the research background, and then the process description of the proposed system is shown. After that, in order to figure out how the parameters affect the system's performance, the optimization is studied along with sensitivity analysis. Further, the exergy analysis of the system is discussed, and by this, the meaning of the coupling system can be found more clearly. And finally, the conclusions are made in the end. So let's begin with the research background. The renewable energy is coupled with the urgent need for environmental protection, like the solar, the wind, the biomass, and the geothermal. However, these renewable energies are usually unstable and intermittent. Like the solar irradiance and wind speed can vary greatly over hours or days. To offset these drawbacks, there are 2 main solutions. One is the integration of various renewable energy sources, like solar and wind, solar and biomass, and so on. Another solution is energy storage system, which is usually used. For instance, the pumped hydro energy system, the compressed air energy storage system, and the liquid air energy storage system. Among these, the liquid air energy storage system, what we usually call LAES, have some characteristics, such as being free of geographic conditions, owing to high energy density and the potential for bulk energy storage, draw more and more attention these days. So today, our study will on LAES. The concept of LAES system is firstly proposed in 1977 by Smith, and with 40 years of development, it has a capacity of about 50 megawatts in 2020. In LAES working process, it has charging, storing, and generation these 3 modes. In charging mode, the compressors are driven by electricity, and the air is pressed to high pressure and high temperature. After transferring heat to oil, methanol, and propane, the cold air passes the GT valve and becomes the liquid air. In storing mode, the energy input during charging mode is stored in the liquid air and the thermal medium. And during the generation mode, the liquid air will be reheated by this medium and then delivered to expanders to generate. However, the traditional LAES system only utilizes the electricity. The cooling capacity and heating capacity are always ignored. But now the multiple energy LAES system will offset this defect. In our work, we choose the multiple energy LAES system, and we will use especially the cooling capacity and electricity in it, which the hydrogen liquefaction just needs. Hydrogen is expected to be an important future clean transport fluid. Although the physical storage or material-based storage waste in the absence of a pipeline network, liquid hydrogen is the most effective way for high energy density and easy transportation. The hydrogen liquefaction cycle is mainly divided in 2 categories, the Linde-Hampton cycle and the Claus cycle. The Linde-Hampton cycle, owing the simple plant and reliable operation, is always used in small and medium size. On the contrary, the Claus cycle is always used in the large cycle, and most exciting plants are based on the Claus cycle. Most exciting plants today are modified Claus cycle with also to Perry conversion, the layout cryogenic cycle, and the refrigerants for pre-cooling and cryogenic cycle. The layout cryogenic cycle has a normal modification. It is to use a separate closed expander refrigerant cycle instead of extracting some hydrogen from the feedstream, which is often called Breton cycle. And the refrigerants are pre-cooling and cryogenic are partly shown in this chart. We can find that the liquid nitrogen the hydrogen, the helium, and some of the organic refrigerants are popular. However, among these, the hydrogen Claus cycle with liquid nitrogen is the most typical choice for the hydrogen liquefaction. Thus, considering the hydrogen liquefaction and LAES system are two critical components of the future energy supply network, we proposed a coupling system that combines these two. Aim is to reduce the energy consumption of the hydrogen liquefaction, which is very important to a liquefaction cycle, and at the same time realize the external delivery of multiple energy vectors in LAES. And in the second section, I will introduce the process working mode and the characteristics. The novel system has three parts: the energy generation, the multiple energy LAES, and hydrogen liquefaction. During the day charging time, the electricity is used to run compressors in the air liquefaction and hydrogen liquefaction. The cooling capacity is supplied from LAES to hydrogen liquefaction by propane and methanol. During the discharging time, the liquid air in LAES is reheated and then expanded to generate electricity, and the stored cooling propane and methanol in the tank will supply to hydrogen liquefaction. Thus, the constant power input and stable operation of hydrogen liquefaction are guaranteed. For the hydrogen liquefaction layout, we choose the typical Claus cycle here with a capacity of 5 tons production per day. There are two characteristics of the proposed hydrogen liquefaction subcycle. The first is the cascade utilization of cooling capacity. In the traditional hydrogen liquefaction cycle, liquid nitrogen is used for pre-cooling from 300 Kelvin to 8 Kelvin. However, in the proposed cycle, pre-cooling is achieved by methanol and then the next propane to finally 80 Kelvin. The cascade cooling capacity from multiple LAES is delivered and utilized in hydrogen liquefaction, which will improve the performance of pre-cooling heat exchangers. The second is the auto-to-power hydrogen conversion reactor. We lay one in the pre-cooling section and two in the cryogenic section, assuming the reaction is like this, and the conversion is just as related with temperature. After designing the system, the optimization is started to decide some important parameters for the coupling system. Let's move to the third section. Before optimization, the objective function and the variables of optimization should be clear. For the hydrogen liquefaction cycle, the pressure before expansion and the mass flow of Claus cycle and GT cycle is important. And for the LAES cycle, the mass flow for propane and methanol extracting to pre-cooling hydrogen is important, so we choose these four parameters as the optimization variables. For the objective function, three indices are commonly used in the performance evaluation, which are the specific energy consumption (SEC), the coefficient of performance (COP), and the exergy efficiency (EXE) that can be calculated as shown. Here we choose specific energy consumption (SEC) to minimize the energy consumption in hydrogen liquefaction. We choose the optimizer in Aspen Hess's software, and with the constraints that the minimum temperature approaches in heat exchangers should be larger than 1 Kelvin. The specific energy consumption of the optimized case is 8.74 kilowatt-hour per kilogram liquid hydrogen, and the exergy efficiency of the optimized case is 32%. Compared with the base case, the energy consumption is decreased by 21%, and the exergy efficiency is increased about 27%. Compared with the other three hydrogen liquefaction with Claus cycle, the energy consumption of the optimized case is lower, and the exergy efficiency are higher than that of ingolated and lunar and lower than that of Kuzumanka. The heat exchanger is one of the most important equipment in the hydrogen liquefaction process. The proposed process has 8 exchangers, so it is necessary to analyze and compare the heat transfer curves. The left is the curve of precooling heat exchangers, and the right is that of cryogenic heat exchangers. The larger the gap between hot and cold component curves, the greater the exergy losses there will be. It can be concluded from the figure that the temperature matching of heat exchangers in the optimization case is better than that of in the base case. The reason for this better matching is because the temperature of each K node has been optimized, and this better matching will improve the exergy efficiency of the system. Although we get the optimal case, the operating parameters in the process will directly or indirectly affect the overall process performance. In order to distinguish the influence of these parameters, the sensitivity analysis is developed. The pressure of circulating hydrogen, the ratio of refrigerants in Claus cycle and GT cycle, the mass flow of propane and methanol are selected to be analyzed. We can find in this fourth figure, exergy efficiency and COP decreased with the increase of circulating hydrogen pressure, while the energy consumption have the opposite trend. This is because as the pressure increases, the power consumption of the compressors will increase. And the second figure shows the COP and EXE increases with the ratio increase. However, the SEC will decrease. This is because of the different working temperature range of the Claus cycle and GT cycle. And from the third and fourth figures, we can find that with the increase of 2 percooling refrigerants, the energy consumption is decreased, and the exergy efficiency and the COP are increased. The mass flow of propane affects pressure. Until now we have achieved the discuss of optimized case and sensitivity analysis. The effect of key parameters is clear. The next selection is the exergy analysis. The independent LAES, independent hydrogen liquefaction, and the coupling systems exergy analysis are discussed. The exergy flow diagram of independent LAES is shown in this figure. We can find that when the input is 33 MW electricity and 300 water cooling, the output is about 27 MW electricity, and the exergy efficiency is 43%. This slide shows the simplified version of the exergy flow diagram of the independent hydrogen liquefaction. The system needs 1.9 MW electricity and the pre-cooling about 0.42 MW. However, the production is only 800 watt electricity and 0.85 MW liquid hydrogen. The exergy efficiency of this cycle is about 37%. Now, when our proposed cycle coupling these two independent systems, the exergy efficiency is 41%. It is very little lower than that of independent LAES, just about 3%. But compared with independent hydrogen liquefaction exergy efficiency, it has a great improvement. By this analysis, the improvement of exergy efficiency by this coupling system is provided. Now, let's discuss the energy saving of this coupling system. When we ensure the production is both 10 ton liquid hydrogen and 100 MW electricity every day, for these two independent LAES and hydrogen liquefaction cycle, the need for input is 33 MW electricity. But the same production for the coupling system, the need of input is only about 54 MW electricity. The coupling system helps save about 14% of energy input. The advantage of this coupling system is proved again. Okay, after the results shows that the proposed system improves the exergy efficiency of hydrogen liquefaction, and at the same time, by using the cooling capacity in multiple energy LAES, the energy consumption is saving. Until now, we have discussed the proposed description, the optimization, the sensitivity analysis, and the exergy analysis. Let's make conclusions about this work. First, we proposed a novel cycle that combines LAES with hydrogen liquefaction. Second, the optimization of the cycle shows the preceding cycle reduces the energy consumption of hydrogen liquefaction. Third, the exergy analysis proves that the utilization of multiple energy from LAES improves the exergy efficiency of the system and helps the saving the consumption of liquefaction cycle. Fourth, the effect of parameters is more clearly after sensitivity analysis. That's all. That is the end of my presentation. And thanks for your listening. And welcome to ask any questions about it.